Some years ago, I was visiting Paris and walking along the Seine River during a beautiful summer afternoon. I saw giant bubbles floating on the riverbank like this one. The next moment, it pops and were gone. Making them were two street performers surrounded by a crowd. They visibly make a living by asking for donations and by selling a pair of sticks tied with two strings. When I was there, a man bought a pair of sticks for 10 euro, which surprised me. I am a scientist who is passionate about bubbles. I know the right tricks to make the giant bubbles is the right soapy water mixture itself. Not in the sticks, which may be needed, but you can easily make it at home. Focusing on the sticks makes us not see that the real tools is the bubbles itself. Bubbles might seem something just children make while playing, but sometimes it can be really stunning. However, there are more fascinating sides to bubbles, such as a problem-solving tools. So, I would like to share with you a few stories about the science of creating bubbles and the science of eliminating the microscopic one. Since it's up on the screen, let's start with the soap bubble. It is made from a very common substances: air, water, soap in the right mixture. You can see soap bubbles constantly changing their colors. This is due to the interaction with light at various directions and the changes of their thickness. One of the common substances, water molecule, is formed by two atoms of hydrogen and one atom of oxygen, H2O. On most surfaces, water droplets tend to curve inwards, forming a semi-hemisphere shape. This is because the water droplet surface is like an elastic sheet. The water molecule on the surface constantly being pulled inwards by the molecule at the center. And the quality of the elasticity is what we call surface tension. Now, by adding soap, what happens is the soap molecule reduces the surface tension of water, make it more elastic and easier to form bubbles. You can think of bubble as a mathematical problem solver. You see it relentlessly trying to achieve geometry perfections. For instance, a sphere is the shape with the least surface area for a given volume. That's why a single bubble is always in a shape of a sphere. Let me show you. Check it out. This is a single bubble. When two bubbles touch each other, they can save materials by sharing a common wall. When more and more bubbles are added together, their geometry changes. These four bubbles are added together. They meet one point at the center. When 6 bubbles are added together, a magical cube appears at the center. That is surface tension at work, trying to find the most effective geometry arrangement. Now, let me give you another example. This is a very simple probe. This is made from 2 layers of plastic with 4 pins connected to each other. Imagine these 4 pins represent 4 cities that are equally apart. And we would like to make roads to connect these 4 cities. My question is, what is the shortest length to connect these 4 cities? Let's find out the answer by dipping it into the soapy water. Remember, the soap bubble film will always try to minimize their surface area with a perfect geometry arrangement. So, the solution might not be something you expected. The shortest length to connect these 4 cities is 2.73 times the distance between these 2 cities. Now you got the ideas. The soap bubble film will always try to minimize their surface area with a perfect geometry arrangement. Now, let us look at bubbles in another perspective. My daughter, Zoe, loves visiting zoos. Her favorite sport is penguin golf at Marwell Zoo in southern England, where she could see penguins swim at speed under the water. One day, she noticed that the body of penguin leaves a trail of bubbles when they swim, and asked why. Animals and birds, like penguin, that spend a lot of their time under the water, have evolved an ingenious way of utilizing the capability of bubbles to reduce the density of water. Emperor penguin, thought to be able to dive a few hundred meters below the sea surface. They are taught to store the air under their feather before they dive, and then progressively release it as a cloud of bubbles. This reduces the density of water surrounding them, make them easier to swim through, and speed up their swimming speed at least 40%. This feature has been noticed by the ship manufacturer. I'm talking about the big ship here, the one that used to transport thousands of containers across the ocean. Recently, they developed a system called air lubricating system, inspired by the penguins. In this system, they produce a lot of air bubbles and redistribute across the whole of the ship like an air carpet that reduces the water resistance when the ship is moving. This feature cut off the energy consumptions for the ship up to 15%. Bubbles can also be used for medicines. It also can play a role in medicines. For instance, as a method for non-invasive delivery system for drugs and genes to a specific part of our body. Imagine a microbubbles filled with a mixture of drugs and magnetic agents being injected into our bloodstream. The bubbles will move to the targeted areas. But how do they know where to go? Because we place the magnet there. For instance, this part of my hand. When the microbubbles move to this part of my hand, we can pop it via ultrasounds and release the drugs exactly where it's needed. Now, I mentioned about the science of creating bubbles, but sometimes we also need to remove them. That's actually part of my job. My exact job title is ink formulation scientist. But I don't work on the ink that you use for your writing pens. I'm working on some cool applications, such as organic photovoltaics, OPVs, and organic light-emitting diodes, OLEDs. Part of my job is to figure out how and why we want to remove the bubbles from the ink that my company produces. During the formulation mixing process, or preparation process, we mix active ingredients, solvents, and additive in order to achieve the formulations with the properties we want when the ink is being used. But just like you make a drinks or bake a cake, it is unavoidable that some air bubbles will be trapped inside those ink. Here, we are talking about different space from the bubbles that I've seen in Paris. The bubbles that trap inside those inks varies between a few millimeters, a few microns, or even a few nanometers in size. And what we are concerned about is the oxygen and the moisture that traps inside. At this size scale, removing them are not easy, but it matters. For instance, for organic light-emitting diodes inks that we can use to produce display for your smartphone, for example. It's supposed to last for many years, but if the ink that we use have been absorbed with oxygen and moisture and are not being removed, then we can quickly see dark spots appear in the pixels. Now, one challenge we face in removing the microbubbles is that they are not very cooperative. They like to sit there, bathing in the ink without moving much. But how do we kick them out? One technology we use is to force the ink going through a thin, long, and tiny tube with a porous wall. And we place the tubes inside the vacuum chamber so that the bubbles can be squeezed out from the ink and being removed. Once we manage to remove the bubbles from the ink that we produce, it is time for celebrations. Let's open a bubbling champagne. Ooh, this is going to be fun. Woo! You could see a lot of bubbles rushing out from the champagne bottles. These are the bubbles filled with carbon dioxide, a gas that's being produced during the fermentation process of the wine. Let me pour some out. I can't miss that chance. I guess it's enough. Here, I can see a lot of microbubbles moving from the bottom of the glass to the top of the champagne. Before it pops, it will jet tiny droplets of aroma molecules and intensify the flavor of champagne, make us enjoy much more the flavor of champagne. As a scientist who is passionate about bubbles, I love to see them, I love to play with them, and I love to study them. And also, I love to drink them. Thank you.